Okay, today I'll show you the basics of Fourier series and Fourier transform. What is this and how you will relate with this. Okay, so what is the Fourier series? Okay, let me clear a few things. There are two types of signals. One is continuous time signal and another one is discrete time signal, right? Continuous time signal, another one is discrete time signal,
District option.
right?
Yes.
And the representation, the analysis of continuous time signal is actually, let me clear this thing again. Periodic and non-periodic signal, right? Two types of
Okay.
mainly periodic signal and
Okay.
non-periodic signal. Okay, non-periodic signal. The thing is, the analysis of periodic signal is the Fourier series.
Okay.
Okay, Fourier series. Remember
So
this. Fourier series.
yes.
Right. Analysis. This is the analysis of an analysis of signal. PS means periodic signal.
There's
Right.
that's
Analysis of periodic signal is called the
Fourier
Fourier series.
series.
And analysis of non-periodic signal is called Fourier
Series.
transform.
Okay.
Transform.
Okay.
Two thing. Remember this thing. This is actually basic thing. Fourier transform. Non-periodic signal. Actually, in real life, we have non-periodic signal, right? Not all of the signals are periodic. So we
Okay.
require Fourier transform. So obviously, there are some other things like Laplace transform. Laplace. Sorry. Let me write correctly. Laplace. Lap. LAC. Laplace. Laplace transform. Another one is Z transform. Right. Z transform. So Laplace transform is used for uh, continuous time signal design, and Z transform is used for discrete time signal design. That is design purpose. That is design purpose. Okay. So Laplace and Z transform, Laplace transform and Z transforms required to design the system. Okay, in time, in continuous time, the continuous time signal or in the discrete time signal. But
Yeah.
Fourier is used to analysis, two things, analysis and design. Okay, this is the basic thing.
Okay.
Okay, try to remember. Okay, so here see the Fourier series. So what it does, Fourier series, actually the analysis of periodic signal. So here the input, we are giving the input in a linear circuit and we are getting the output in a
Outputs.
linear circuit. Okay. So sinusoidal inputs, since it is periodic, non-sinusoidal inputs, no. Non-sinusoidal inputs, if we convert it to the sinusoidal inputs, then it is Fourier series. Okay. So here is the guy, Joseph Fourier. He born in 1768 and died in the 1830.
Okay.
So okay,
Okay.
he died in the 1830. Joseph Fourier. So Fourier studied the mathematical theory of heat conduction. He established the partial differential equation governing heat diffusion and solved it by using infinite series of trigonometric functions. Okay. So he studied the mathematical theory of heat conduction. He established the partial differential equation governing heat diffusion and solved it by using infinite series of trigonometric functions. Okay. So Fourier, he proposed the Fourier series in 1807. So what was his proposal? A periodic waveform, which is ft, could be broken down into an infinite series of simple sinusoids, which, when added together, would construct the exact form of the original waveform. See, see the definition again. A periodic waveform, we are considering a periodic waveform, which is ft. We can break it. We can break it into many small terms. Okay, into a small sinusoidal signals. Okay, in the series of sinusoidal signals, and later if we add them together, then we would get the exact form of the original signal, or the original waveform. That is his proposal. Okay, so try to understand. A periodic waveform, which is the ft, could be broken down into an infinite series of simple sinusoids, which, when added together, would construct the exact form of the original waveform. That is the Fourier series. Okay, so consider the periodic function. Let's consider a periodic function. Ft is equal to f of t plus nt. That means if we shift the signal in the left or right, then here n, value of n is plus minus 1, plus minus 2, plus minus 3, up to infinity. Okay, so if we change, here t is the period. So that means if we shift the signal, then if we add them, then we will get the same signal. Okay, that means signal is periodic. Consider the periodic function. That is the periodic function. Okay, so according to his formula or his proposal, this is same. Okay. Now the expression of the Fourier series. Now how we can express the Fourier series? Let us see. A naught. These are the coefficients. Fourier trigonometric coefficients. Okay. Plus summation of n from 1 to up to n, an cos of n omega naught t plus n 1 to a summation of bn sin n omega naught t. Okay, this is the Fourier series expression. Okay, this is the Fourier series expression. Okay, this is the Fourier series expression where a naught, an, bn, these are real and are called Fourier trigonometric coefficients. And omega naught is equal to 2 pi by t, where we can write this like let me write omega. We can write omega naught is equal to 2 pi f, right? We can write the 2 pi f, where if f is equal to 1 over t, where f is equal to 1 over t. Okay, so f is equal to 1 over t. So omega not equal to 2 pi f, where f is equal to 1 over t. Or alternatively, we can write like this. Okay, where c naught is equal to a naught and cn are the complex coefficients. So Fourier series, what we can say, Fourier series A is equal to a finite sum of harmonically related sinusoids. So both are sinusoidal signals. Both are sinusoidal signals. So if we add several sinusoidal signals, then we can get the Fourier series. Okay. So that is the main expression of Fourier series. Okay, let us go to the next. Okay. Average or DC value of ft. C naught is the average value. For n equal to 1, if we put the n is equal to 1, corresponding sinusoid C1 cos omega naught t plus theta 1 is called the fundamental. And if I put the n is equal to k, then the corresponding sinusoidal signal would be like this: ck cos k of omega naught t plus theta k, where this is called the kth harmonic term. Similarly, omega naught is called the fundamental frequency and k omega naught is called the kth harmonic frequency. So remember this term, which is the fundamental. If I put n is equal to 1, then it would be fundamental term. If I put the n is equal to k, then it would be harmonic term, kth harmonic term, all right? And omega naught is the fundamental frequency, and k omega naught is called the kth harmonic frequency, right? Okay, so that is our another basic concept, which is the fundamental and which is the harmonic term. Okay, if we add few more, then those will be harmonic. First harmonic, second harmonic, third harmonic, fourth harmonic, up to like this. Okay, harmonic term. So if we add the harmonic terms together, then we'll get the main equation or the original equation. Okay, so here is the definition of the Fourier series. But before we have seen the proposal of the Joseph Fourier. Okay, his proposal. But here we have seen the uh, definition. A Fourier series is an accurate representation of a periodic signal and consists of the sum of the sinusoids at the fundamental and harmonic frequencies. Okay, so that is the definition of Fourier series. Is an accurate representation of a periodic signal and consists of the sum of sinusoids at the fundamental and harmonic frequencies. And n tends to infinity. The waveform ft depends on the amplitude and phase of every harmonic components, and we can generate any non-sinusoidal waveform by an appropriate combination of sinusoidal functions. But we can generate the non-sinusoidal waveform also by using this. Okay, so the waveform ft depends on the amplitude and phase of every harmonic components, and we can generate any non-sinusoidal waveform by an appropriate combination of sinusoidal function. Okay, so let's see. So some property we have, let's look at some property of the Fourier transform. Okay, sorry, Fourier series. So to be described by the Fourier series, the waveform ft must satisfy the following mathematical properties. Some properties are there. It should follow this. First of all, ft is a single value function except at possibly a finite number of points. It is a single value function. The integral, that would be the integral of ft. T naught, it will start from the T naught to the ends and the T naught plus T. If T is less than infinity for any integral. Ft has a finite number of discontinuities within the period T. So Ft has a finite number of discontinuities within the period T. Ft has a finite number of maxima and minima within the period of T. So it will have discontinuity at the T period, and it will have a finite number of maxima and a finite number of minima within the period T. So in practice, Ft is equal to Vt or It. So the above four conditions are always satisfied. V means the voltage, I means the current, right? V and I. V means voltage, I means the current. F means the frequency. Okay. Recall from calculus that sinusoids whose frequencies are integer multiples of some fundamental frequency f naught form an orthogonal set of functions. This kind of set is called the orthogonal set of functions. Like f naught t, we can put the n is equal to 1, 2, 3, 4 up to anywhere. So 2 by t, that means 2 multiplied by 2. Okay. And let's say 0 to t, 0 to t, sine 2 pi n t by t, sine 2 pi m t by t is dt is equal to. So we can write like this, cos. If we move, so we can write it as a cos also. Both are same. So 0 here, the result would be 0 if n is not equal to m, and result would be 1 if n is equal to m but not equal to 0. Then result would be 1. Okay. This is the orthogonal property. Okay, so the Fourier trigonometric coefficients can be obtained from a naught 1 by t, t naught to the t naught plus t ft dt average value over one period. A n is equal to 2 by t, t naught to t naught plus t ft cos n omega naught t dt, n is greater than 0. Bn is equal to 2 by t, t naught to the t naught plus t ft and omega naught t dt, n is equal to 0. Okay. So these are the trigonometric coefficients. Okay, we can write these coefficients. A naught, if I write the A naught means 1 over T naught, integration of T naught to the T naught plus T. Okay, these are the Fourier series, Fourier trigonometric coefficients. Okay, so if I want to find out the AK, okay, A to the power K, then what would happen? See this. 0 to t, 0 to t integration, the range 0 to t. Okay. Ft cos k omega naught t dt is equal to 0 to t a naught cos k omega naught t dt. So plus, so summation, this is the summation here. Okay, the only non-zero term is for n is equal to k, non-zero term, ak t by 2. A similar approach can be used to obtain bk. So similarly, similar approach can be obtained. Okay. So here see, determine the Fourier series and plot for n equal to 7. Fourier series. So determine the Fourier series and plot for n equal to 7. Here is example. This is a rectangular wave. This is a rectangular wave. Range is minus t by 4 to the t to the t by 4. Okay, that is the range. So what is the maximum amplitude? 1. So what would be the average DC value? Half, right? Average is half. So A naught is equal to, this is the equation. So minus t by 2, minus t by 2 to the t by 2. Minus t by 2 to the t by 2. This range, ft. Okay, here we have to cover both things. Okay, so 1 by t minus t by 4 minus t by 2 minus t by 4 to t by 4. This range, this is 1, ft is equal to 1, right? Here 0, but here 1 dt. So that means what? That means half d dt. So t to the t by 4 minus t by 4. So it would be half. Okay. So it would be, result would be half. So A naught is equal to half. You understand? How you have to find, you find out the A naught. So we know that A naught is equal to 1 over t naught, t naught plus t. So here the t naught minus t by 2 to the t by 2. Okay. And the range, they have found that this one. An even function exhibits symmetry around the vertical axis at t is equal to 0, so that ft is equal to minus ft. So bn is equal to, this is the function, the equation of bn, t naught to the power integration t naught to the t naught plus t. So minus t4 to t by 4. Here 1 sin n omega naught t dt. So the integration here, if I put the n is equal to, so here the integration would become the 0. Only an, this is the equation of an. Okay. So 1 by n pi. So some calculation is there. N is equal to 0, and n is equal to 246. Okay, and n is equal to 2 into minus 1 whole to the power q by pi by n, where q is equal to n minus 1 by 2. That is the Fourier transform of this, that signal. That is the Fourier transform. Sorry, Fourier series of that given signal. Okay, that is the Fourier series. Okay, so symmetry of the function, 4 type: even function symmetry, odd function symmetry, half wave symmetry, quarter wave symmetry. So even function f of t is equal to f of minus t. Here an is equal to 4 by t 0 to t by 2 f of t cos n pi omega naught t dt. And the odd function, it would be f of t is equal to minus f of minus t, n is equal to 0. That is the equation. Half wave symmetry, that is the half wave symmetry equation. And quarter wave symmetry,
Yeah.
okay. Some examples are there,
Yeah.
they have given, and even in quarter wave. So they said this, okay. And determine Fourier series and n is equal to question, what is the value of n? So it is the triangular shape wave. So Fm is equal to 4 and t is equal to pi by 2 second. Fm is equal to 4, t is equal to capital T is pi by 2, period is the pi by 2. So t is equal to pi by 2, so omega naught is equal to pi by t is equal to 4 radian per second. Because if you put the t's value, it would be 4, right? If you put the t's value. To obtain the most advantageous from a form of symmetry, choose t1 is equal to 0 second, t1 is equal to 0 second, odd and quarter wave, and all an is equal to 0 and bn is 0 for even values of n and a naught is equal to 0. So bn for odd n, and ft, fm by t by 4 t, do the calculation. Okay, so 32 t by pi. So bn value of bn, this one for odd n. Okay, so the Fourier series is this one. Uh, 3.24. If you put the value of this, do calculation. For first 4 n terms up to n equal to 7. 1, 2, 3, 4, 5. Next harmony is for n is equal to 9, which has magnitude. Okay, so it will be changes. Okay, like this. So exponential form of the Fourier series, that is the Fourier series. C naught is the average or DC value of ft. Cn, this is the equation where Cn is equal to this equation, and theta n, equation of theta n. Okay. So an is equal to 2 Cn cos theta n, and bn is equal to 2 Cn cos sin theta n. So cos n omega naught t plus theta n in exponential form using Euler identity. So if we can write the exponential form, we can write it to the exponential. Where the complex coefficient are defined as a Cn, where Cn defined as like this. Okay, Ej theta t. And Cn is equal to conjugate of C minus n. The coefficients for negative n are the complex conjugate of the coefficients for positive n. Okay, the coefficients for negative n are the complex conjugate of the coefficients for positive n. Okay, so the complex Fourier series we can find out. So average ft is 0, c naught is equal to 0, cn, this is the equation of cn, t naught is equal to minus t by 2, define j and omega naught is equal to m, and put this value, then finally they have got this one. Okay, so for even n it would be 0, for the odd n it would be this. Okay, and for n equal to 1, if you put the n equal to 1, then you get the value, and n equal to 2 you get this value, and n equal to 3 you get this value. The complex Fourier series, so they have written here. See, e of j, e to the power jx plus e to the power minus jx is equal to cos x, and e to the power jx minus e to the minus jx is equal to j sin x, where k is equal to n minus 1 by 2. For real, ft is equivalent to c of n is equal to c of minus n. Okay, some examples are there. They have given see the Fourier spectrum, the complex Fourier spectrum. This is the amplitude spectrum, and this is the phase spectrum. See, that is the amplitude, and this is the omega frequency, and that is the angle, that is the frequency. So this is the amplitude spectrum, this is the phase spectrum. Two kind of spectrum are there. Okay. So Fourier spectrum is a graphical display of the amplitude and phase of the complex Fourier coefficient at the fundamental and harmonic frequencies. So that is the example of a periodic sequence of pulses, each of with delta. Okay, that is the delta. A is the amplitude. The Fourier spectrum is a graphical display of the amplitude and phase of the complex Fourier coefficient at the fundamental and harmonic frequencies. See, and Fourier coefficients. So Fourier coefficients Cn for n not is equal to 0. This is the equation. Final equation. Just look at the final equation. Okay, so Fourier spectrum Cn we could write like this. Okay. L'Hopital's rule, that is the L'Hopital's rule. And these things are overshoot. This is called the overshoot. Okay. And see, it is often desired to determine the response of a circuit excited by a periodic signal. So in RC circuit, V naught is equal to what? Output voltage. R is equal to 1 ohm, C is equal to 2 farad, T is equal to pi second. And RC circuit excited by a periodic voltage Vs. So it is our periodic voltage. But we have to find out the output. Okay. See, each voltage source is term of the Fourier series of Vs. Okay. Each voltage source is a term of the Fourier series of Vs. F. So Vs naught T, Vs 1T, Vs 3T, Vs 5T. So that is the V naught T. So input and output. Okay. An equivalent circuit of this. Okay. Vs. So Vs 0, 0, Vs 1 by j omega naught c. Vs 3, okay, 1, 3, 5. 3 this one. Vs 5, this one like this. Using phasors to find steady state response to the sensors. Okay, so VST half n is equal to 1, summation of n is equal to 1 odd number to up to n. So that is the formula. So here where k is equal to n minus 1 by 2. The first 4 terms of VST is where omega naught is 2 radian. So first 4 term VS0, VS1, VS3, VS5. Okay, just change the value 1, 3, 5. What would be the value of 1 pi? If you put the value by here n is equal to 1, it would be 0. That is n cos 2t, that means 1 omega t. Omega naught. Let's put the values, then you'll get it. And the minus 3, 1, 3, 5. Put those values, then you will get it. Okay, the steady state response V naught can then be found using superposition. Okay, by using the superposition, we'll find the value of V naught. And the impedance of the capacitance, impedance also can be determined. So in this slide, we have seen the Fourier series, symmetry of this function, exponential form of the Fourier series, the Fourier spectrum, the truncated Fourier series, the Lagrange Fourier series. Okay, let me show another one. Okay, some basic signal idea. Some basic signal idea which is also required here. Okay. So periodic and aperiodic signal. Periodic signals are such that x of t plus t is equal to x of t for all t. The small set value of t that satisfies the definition is called the periodic. That is the period. Below on the left, below on the left below is an aperiodic signal with a periodic signal shown on the right. So that is a periodic signal, and this is the periodic signal. Okay, that is the T, the period. A right-sided signal is 0. That is the 0 signal. T is less than, T is greater than, this T is greater than small t, then it would be 0. But left-sided signal is 0 for t is greater than small t. Small t is greater than t, then it would be 0 here, right? Here it would be 0. And bounded and unbounded signal, this is the bounded signal, this is the unbounded signal. Even an odd signal, we have also seen this. Even signals xc of t and odd signal x naught of t are defined as x of t is equal to xct. Okay, this is even an odd signal. And real and complex signals, an important class of signals are continuous time signals of the form xt of est, discrete time signals of the form x of n, z of n, where z and s are complex numbers. Here z and s are complex numbers. For both exponential ct, continuous time signals and discrete time signals, x is a complex quantity and has a real and imaginary part, or a magnitude and an angle. What is the most convenient depends on this analysis. Okay, so for example, suppose s equal to j pi by 8 and z is equal to j pi by 8, then the real parts are real parts and imaginary and real parts. Okay, so why do we need the Fourier analysis? See, in communication, we send and receive information signal over a medium. The medium and the hardware corrupts the signal. The receiver has to extract the information from the corrupted signal. The transmitted signal have well-defined spectrum contents. So if the receiver can do a spectrum analysis of the received signal, then it can extract the information. See, that is why we need the Fourier analysis. Sometimes we may be confused. What is the necessity of learning Fourier analysis? So in the communication system, we need the Fourier analysis to extract the information from the transmitted signal. Okay. So Fourier analysis can look at an unknown signal and do an equivalent of a chemical analysis, identifying various frequencies and their relative quantities in the signal. So the Fourier series. So any periodic power signal, see, any periodic power signal is equal to infinite sum of sines and cosines at different frequencies. This is the Fourier series. So we know that linearity property, we already have seen this before. Scaling, that is the scaling, and exponential representation, periodic or form, two-sided amplitude spectrum. Okay. See the Wt is equal to summation of minus infinity to infinity Wm e to the power j2 pi nt by t naught. This is a signal. We already seen this before. So Fourier series of periodic signal of finite amplitude spectral components separated by discrete frequency intervals of f naught equal to 1 by t naught. So it has this finite amplitude and it has a interval, that is the period. It should have a period. Okay. So Fourier transform property, Fourier transform. See, Fourier transform, Fourier series of periodic signals. So it is a transformation. So if Wt is real, then W minus F is equal to conjugate of WF minus. If WF is real, then Wt is even. If WF is imaginary, then Wt is odd. Linearity, time delay, scaling, duality. So Fourier transform represents a periodic function as a continuous summation of sines and causes. Fu f of x e minus j2 pi ux. Okay, so ux vy.
Sir.
We'll explain it later, details. Okay, Fourier transform. Today I have explained only the Fourier series. Okay, already see some things are there like continuous CFT means the continuous Fourier transform. Okay, Fourier transform is required in the discrete non-periodic signals, right? In the non-periodic signals, we require the Fourier transform, continuous time signal and discrete time signal Fourier transform. Okay, and the analysis we need the Fourier transform. So I think we'll check it later details. Okay. Some other things are also there. Basic things. Okay, so today not many persons are there.
Okay,
Only
sir.
few. Yes.